organic reactions, and there'll be a part 2 next week. As always, copy all of this into your notebook. Use the spacebar to start and stop as needed. Okay, now I'm going to show you a graphic here. Do not copy this down or freak out. It looks a little confusing. This is referred to as a reaction pathway. And you can see that you have many of the compounds that are listed here, alkane, halogenoalkane, alcohol, you've seen before. But what we're going to be looking at today is how one of those types of organic compounds can be converted into another. Next to the arrows, you can see reactants that are needed, or a catalyst that's needed, or a particular process like distillation that's necessary for the reaction to take place. Now, we're only going to be looking at these reactions in a very, very simplistic manner. Next week, we'll take a couple of these reactions and kind of pull back the curtain and look at them in much more detail. Okay, the first, substitution reactions, when one or more atoms replace another. An example, halogenation. In a halogenation reaction, we have an alkane that reacts with a halogen. We're just using chlorine as an example. Now, in order for this reaction to take place, we need ultraviolet light, and that will be the energy that's necessary to break the bond between the two chlorine atoms. Now, in fact, this will be one of the reactions that we'll look at in much more detail next week. Now, in this reaction, one of the chlorines is going to be replacing one of the hydrogens in the alkane, so it's substituted in. So we can see that here, or we now have a halogenoalkane. So the term substitution it is exactly that. One atom is being substituted in for another atom. So anytime you see a reaction where the organic molecule, one atom has been lost and another atom has taken its place, it's a substitution reaction. Now, it need not necessarily be just an atom. This could be the hydroxyl group or an amine group or something like that. But anytime one thing replaces another in a compound, it's a substitution reaction. Addition reactions, when atoms are added across a double bond. An example of this, hydrogenation or hydrogenation. Now, we need to have an alkene in order for this reaction to take place. What will happen is one of the bonds in the double bond will break, meaning that each of the carbons will have to bond to something new, hence the term addition. We're going to add something to the molecule. So in this reaction, the hydrogen is going to be added to each of the carbons. So we had CH2 with a double bond, now we have CH3 with a single bond. So addition reactions, again, the term is very descriptive. We're adding something to the molecule. In order to add something, we have to have a double bond that breaks in order to latch on to the new atoms. For this reaction, we need either nickel or platinum as a catalyst and need to heat it up. Steam is used for this reaction. Another example is hydration. For hydration, we'll have our alkene react with water. The catalyst is phosphoric acid, and this will form an alcohol. One of the carbons now had two hydrogens, now it has three. Has two hydrogens, now it has a hydroxyl group. So we've added water across that double bond. Hydrogen to one carbon, hydroxyl to the other. Okay, now this is a kind of a summary of what we just talked about, but there's a couple of new things in here too. So this you've already seen, this you've already seen, but this is new. So we have an alkene reacting with a hydrogen halide. Now typically, well, X means either is a halogen, either fluorine, chlorine, bromine, or iodine. Typically, when we see hydrogen with one of these guys, it's an acid like hydrochloric acid, hydrobromic acid. But in this case, it's a gas. In its pure form, they're gases. Just place them into water and they become acids. But anyways, so if we had a hydrogen halide reacting with an alkene, we'll have the hydrogen and the halide be added across the double bond. So this is an addition reaction. Now this is referred to as hydrohalogenation. if we were to add the halogen itself, which are diatomic, each of the halogen atoms would be added across the double bond, and this is called dihalogenation. Dihalogenation. Okay, the bromine water or saturation test used to distinguish between alkanes and alkenes. Now remember, alkanes are saturated hydrocarbons, meaning that they have the maximum number of hydrogens possible, and alkene and alkyne are unsaturated. We can break the double or triple bond to have more hydrogens added to the compound. This is a test to simply distinguish between the two, an alkane or an alkene. Now I'm kind of start this video. Oops, no. Let me start this video. All right, now what they're adding here is what's called bromine water. So bromine water. Now bromine is a liquid, but that's not what this is. Bromine is slightly soluble in water. It has a very distinctive orange-brown color, as you can see here. So when we pour the bromine into an alkane or an alkene, we'll see a different reaction taking place. Okay, now you can see that the beaker on the right, the color has gone away, indicating that it is our alkene, in this case pentene. The color remains if it's an alkane. I think they add some more here. Okay, so the test is that if the color from the bromine water disappears, it's an alkene. If it remains, it's an alkane. So let's look at a couple of examples. So if we add the bromine water, which would be aqueous, to an alkene, what will happen is, well, the bromine has that orange-brown color, and that's what we're interested in. The color goes away, and what the compound that results is a 1,2-dibromoethane. The bromine has been added across the double bonds. So in other words, the brown color that came from bromine disappears because bromine no longer is present. It's now part of this organic molecule that doesn't have a color. Now, if we put the bromine water into an alkane, there'll be no reaction. And we know that there's no reaction because the color remains. So it's just a real simple test to see whether or not we have an alkene or an alkane. If it's an alkene, the color from the bromine water will disappear. If it's an alkane, the color from the bromine water will remain. Elimination reactions, when atoms are lost, results in a carbon-carbon double bond. Example, dehydrogenation or dehydrogenation. So we have an alkane. The catalyst for this is either silver or vanadium oxide. And this will form an alkene and hydrogen. Now, of course, this is just exactly the opposite of an addition reaction. An addition reaction is going in the opposite direction. So, and that, remember, that would have been referred to as hydrogenation. So this is dehydrogenation. Dehydration, we're going to take an alcohol, typically an alcohol. Catalyst for this is sulfuric acid, and this will remove the water. So in an elimination reaction, atoms are removed, which means that the carbons that we're holding onto those atoms are forced into having to have a double bond between them. Condensation reaction, the combining of two organic molecules that results in the loss of a small molecule as a product, usually water. So example, esterification, which is the formation of an ester. Now, in an esterification reaction, we'll have a carboxylic acid reacting with an alcohol, and this will form an ester and water. The catalyst is sulfuric acid and heat. And again, I think I mentioned this before, this is a reaction that you would have done in class. You would have picked a certain carboxylic acid, a certain alcohol, heated it up, added some sulfuric acid to create an ester that would have a particular fragrance. Okay, so let's look at an example. So this is a carboxylic acid, ethanoic acid. This is an alcohol, ethanol. And what happens is that the hydrogen from the ethanol and the hydroxyl from the carboxylic acid, under these conditions, the sulfuric acid and heating it up, will break away, which means that this carbon is going to have to bond to this oxygen. So it splices these two molecules together. But in so doing, it loses these atoms. So this will form our ester, so the carbon bonded to the oxygen, and water is a byproduct in this reaction. Now, it says that in these reactions, a small molecule will be formed as a product, usually water. The other molecule that's common is ammonia. So if this was an amine, then this would form ammonia. So if this was a carboxamide, we would have NH2 here and H forming ammonia. Combustion reactions. Combustion of hydrocarbons and alcohols. These are the only two that you need to know, and they both have exactly the same products, carbon dioxide and water. So any hydrocarbon bringing in oxygen if it was an alcohol. If we burn them, we'll have these two products. Examples, we burn methane, carbon dioxide and water. If we burned methanol, I thought I'd give you a chance to practice balancing equations. This one takes a little bit of thought. Why don't you pause the video, see if you can balance it. Okay, the coefficients are 2, 3, 2, 4. Did you get it? Good job. Now we have incomplete combustion. Incomplete combustion occurs when there is insufficient supply of oxygen, resulting in carbon monoxide and carbon also being produced. So we still produce carbon dioxide and water, but also carbon monoxide and carbon. Okay. Now, carbon monoxide is very dangerous. It has no odor, and your body will absorb the carbon monoxide rather than oxygen. So when you breathe in, if you breathe in carbon monoxide, your blood will, the hemoglobin in your blood will latch on to the carbon monoxide much more readily than it would oxygen. So you quite quickly asphyxiate. So it's particularly dangerous because it has no color, has no odor, so you don't even know that you're breathing it in. So that's why you should have a carbon monoxide detector in your home. The carbon, anytime you see smoke being given off in it's when something is being burned, like in a fireplace, that is carbon, or the exhaust from a car, that black smoke that comes off, that's carbon. Oxidation of alcohols. Yes, oxidation, it's back. An organic compound is oxidized whenever a carbon-oxygen bond is added. So either an oxygen is bonded to a carbon, or it goes from a single bond to a double bond. That would be oxidation. Okay, we're going to look at the oxidation of primary, secondary, and tertiary alcohols. The oxidation of a primary alcohol, in order for the reaction to take place, we need to have heat and what's called a strong oxidizer. Dichromate is a strong oxidizer. It has a distinctive orange color. It's actually quite pretty. The other strong oxidizer that's often used is permanganate, MnO4 with a -1 charge. And so as you can see, these strong oxidizers have a lot of oxygens in it. Now, in this reaction, going from a primary alcohol to an aldehyde, we have a single bond to an oxygen going to a double bond to an oxygen. Hence, the molecule has been oxidized. If we continue to heat the aldehyde in the same conditions, we form a carboxylic acid. So again, we have an addition of a carbon-oxygen bond. This carbon was just double bonded to an oxygen. Now it still has that double bonded oxygen, but it also has the hydroxyl group. So it has another carbon-oxygen bond. Okay, now in this reaction, when the primary alcohol is oxidized to an aldehyde, that reaction is taking place. Now, as soon as the aldehyde forms, it's in the same conditions and it can be oxidized into a carboxylic acid. So we have, when this reaction is taking place, we have both of these taking place simultaneously. But what if we just wanted the aldehyde? How could we prevent the aldehyde from being converted to carboxylic acid? To do that, we take advantage of the fact that aldehyde has a much lower boiling point than an alcohol or a carboxylic acid. Alcohols and carboxylic acid have hydrogen bonds between their molecules, but aldehydes are relatively nonpolar, and so they have much weaker dipole-dipole forces of attraction between their molecules. So aldehydes have low boiling points and can be removed by a process called distillation, preventing the formation of the carboxylic acid. So distillation looks like this. So in the flask here, we have our primary alcohol that and the dichromate. So the reaction is taking place, the alcohol is being converted to an aldehyde, and the aldehyde would immediately be converted into a carboxylic acid. But because the aldehyde has a lower boiling point, it turns into a vapor. And what we can do is take advantage of that by collecting the vapor outside of the flask. And so as the aldehyde forms, it turns into a vapor at the temperature that it's set at, and it goes through this tube here. This is called a condenser. And so water, it just flows through the tube. Now it doesn't actually mix with anything. It just cools off the gas, and it is collected outside the flask, preventing it from reacting to form carboxylic acid. Now, if we wanted the carboxylic acid, we use a process called reflux. Now, for reflux, it's like taking this condenser here and putting it on top of the flask. So what happens here is as we heat the mixture, once the aldehyde forms, it will rise up in the tube here in the neck of the flask, but it's cooled off. So again, we have our condenser here that just cools off the gas, causing it to convert back to a liquid, and it simply drips back down. It's kind of a cool thing to see. You have a boiling taking place here. You can see that the vapor is rising up, but somewhere in this condensation tube, it converts back to a liquid, and this just trickles back down into the flask. So you see a liquid dripping back into the flask at the same time that boiling is taking place. So simply put, the vapor is never allowed to escape, and so then the vapor would be aldehyde. So the aldehyde is being forced back into the flask to be converted to carboxylic acid. Secondary alcohols. Secondary alcohols also can undergo oxidation, same conditions, dichromate and heat. And this will form, though, a ketone. So this is our secondary alcohol. Remember, what makes it a secondary alcohol is the carbon that's bonded to the hydroxyl group is bonded to two other carbons. So when we go from a single bond to a double bond, it's oxidized, but in this case, rather than it being an aldehyde, it's a ketone. Now, if we continue to heat the ketone, same conditions, nothing will happen. So no further oxidation will take place. So for a secondary alcohol, it's just a one step. It'll be converted to a ketone. For a tertiary alcohol, so even easier, under these conditions, no reaction will take place at all. So what you need to know is a primary alcohol can be oxidized to an aldehyde and then to a carboxylic acid using distillation to separate out just the aldehyde, reflux to have the reaction go to completion to form carboxylic acid. A secondary alcohol can be oxidized to a ketone, but nothing further, and a tertiary to nothing at all. And by the way, in these reactions, you'll notice that we're not really paying careful attention to it being balanced. So for example, here, when the carbon goes from a single to a double bond, what happened to these hydrogens? Well, we're generally not interested in that in these looking at synthesis reactions where we have one reaction be converted into another. Kind of our focus is on the organic molecule itself. So this one went from being a secondary alcohol to being a ketone. So the other elements that are involved in the reaction are kind of byproducts that we're not really interested in. Next, addition polymerization of alkenes. An alkene can undergo addition reactions with itself to form a long chain polymer containing many thousands of carbon atoms. So simply put, we have carbons that are double bond. If we break one of those double bonds, and by the way, remember that a double bond is both a sigma bond, which is the sharing of electrons that's axial between the two carbons, a straight line between the two carbons, but the additional bond is a pi bond that goes both above and below the sigma bond. And the pi bonds are the ones that are most susceptible to being broken. So in this reaction here, the pi bond is broken, which means that each of the carbons now need to bond to something else. And we can form links in a very, very long carbon-carbon chain. So this is referred to as a monomer. And if we break the double bond and splice them together, we have what's called a polymer. Now, writing it like this is a little cumbersome. There's a simpler way of doing it, where we use brackets to represent the repeating unit. So the number of monomers that we have is represented by N, and so N here is the number of repeating units. So if we had 1,000 monomers, then this would be 1,000 links in the chain. Now, when you draw your polymer, you need to make sure that the bracket bisects the bond. You don't want to have that entire bond inside the bracket because we need to indicate that it is just a link in the chain. If you were to take the IB exam and were asked to represent the polymer, and you were to include the single or the bond to the carbons inside the brackets, you wouldn't get a point for that. Okay, a little bit more about polymers. Polymers are large organic molecules consisting of many repeating structural units called monomers, connected together by strong covalent bonds. Remember, carbon-carbon bonds are very, very strong. So that's why you can have these really long chains of polymers. Other atoms just can't do that. Some natural polymers, carbon, silk, wood fibers are all natural polymers. Synthetic polymers, Teflon, nylon, celluloid. Now, celluloid is the first plastic. We'll talk more about plastics in a minute. It was invented or created around 1870. It didn't really have much use. It wasn't a very useful type of plastic as we think of them now. But about 30 years later, it found a use that took off big time. And that was in movies. And you may have heard that sometimes movies are referred to as celluloids. Now, they stopped using celluloid in like the 1960s, somewhere around that 60s, 70s. And all the movies before that, though, were filmed on celluloid plastic. There was a problem with that, however. It begins to decay after a while. And many of the older movies, back, the silent movies, the movies from the 20s, 30s, 40s, began to deteriorate, and there was a frantic effort in like the 1980s and 90s, mostly in the 90s, to digitalize the movies or to restore them. Anytime you see old movies that look kind of choppy and you see kind of specks or something floating around in the movie, that is because the celluloid just decomposes after a while. At the time the movie was made, it was beautiful. Those silent movies that just look awful, back in the day, they were gorgeous. It's just the ravages of time. A plastic is a polymer that can be heated and molded while relatively soft. And so it's a little animation of this. So you have your plastic powder being injected and heated up and then pressed into some sort of mold. And here, they're making some sort of dinosaur. So it's a plastic. Now, I'm sure that you know there's many different types of plastic. If ever you've gone to recycle plastics, you know that there's different bins for different types of plastics. I'll put a link on the uh, our Google Classroom for this. It's a nice little graphic of the different types of plastics: polyethylene, polypropylene, polypropylene, nylon, polyurethane, etc., and what the monomers are for each one of those. The monomers completely determine the type of plastic that you have. Okay, I thought I'd overshare with you here maybe a little bit. This is a classic line from the 1967 movie The Graduate. The line starts, I want to say just one word to you. Now, at the time when this movie came out, this line was just really funny. I'm not sure it holds up anymore, but why don't I show you this movie clip? You're going to see a very, very young Dustin Hoffman.
I was going to go upstairs for a minute.
Oh, I meant with your future. Your life.
Well, that's a little hard to say.
Ben.
Excuse me. Mr. McGuire.
Ben.
Mr. McGuire.
Come with me for a minute. I want to talk to you. Excuse us, Joanne.
Of course.
Please.
It's just incredible. I look at him and I can't believe it.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
I've said. That's a deal.
Okay, so the reason this was so funny, back in the 1960s, plastic was just taking off. You don't know of a world where plastic isn't everywhere. But back in the 1960s and prior to that, plastic was kind of a novelty and kind of thought mostly just really cheap, and I guess maybe to some extent it still is. But it was not as ubiquitous as it is today. It's hard for you to just look around anywhere and you don't see plastic everywhere. A good example is car dashboards. These days, virtually any car is entirely plastic, their dashboard. But back in the 60s and prior to that, it was mostly metal, sometimes wood, sometimes a little bit of plastic, but glass, wood, metal has been replaced with plastic. So at the time of this movie, this was part of the changing world. Plastics were just kind of beginning to become a huge part of our everyday life. Okay, polymer examples. This is ethene, often referred to as ethylene. And this forms polyethylene or polyethylene. This is the most common, simplest plastic there is. Another, this is called chloroethene or vinyl ethene. It has a chlorine that has been substituted for one of the hydrogens. Now the word vinyl refers to this. So we have ethene, except one of the carbons has a bond that's going to be bonded to something. The word vinyl comes from the Latin vinum, which means wine, which has ethanol in it, and this can be derived from ethanol. And so the vinyl is reference to the wine from which ethanol can be extracted, and this can be synthesized. In this reaction, we have polychloroethane forming, or more commonly called polyvinyl chloride. I thought I'd give you a chance to see if you can figure out what is it more commonly referred to as. I'll give you a hint. In Home Depot, if you go there, they'll have aisles and aisles of nothing but this plastic. And it is PVC. So PVC is a very strong plastic, widely used in many applications. It's the world's third most used plastic. So it's used in construction all over the place. You're probably most familiar with it as the plastic in piping, plumbing. And last, tetrafluoroethene, forming polytetrafluoroethene, more commonly referred to as Teflon. It's a brand name. It's widely used as non-stick coating for pots and pans. It has many other uses, but that's one that's everybody's most familiar with. So if you have pots and pans and it has that kind of a dark gray coating, that's Teflon. And again, back to the 60s, this was used. This was a big deal that we finally had pots and pans where things didn't stick to. Okay, that is it. Next week, we'll be looking at some of these reactions in much more detail.